In this section, we'll see that conditional expectation function is actually the best predictor. Suppose that you are given x variable and you want to predict y. What predictor g of x should we use? What functional form of g should we choose? Well, the prediction error when you use this predictor g of x will be given as the difference between y and your predictor. But this prediction error is stochastic. If we come up with a non-stochastic measure of the prediction error, what we can do is that we take the expectation of the prediction error squared, and that measure is not stochastic, and that measure is called mean squared prediction error or mean squared error, MSE. There is a theorem, and the theorem states that when your y outcome's variance is finite, then for any predictor g of x, the mean squared errors of your predictor g of x will be greater or equal to the mean squared error you get when you use m of x as your predictor, where m of x is just the conditional expectation function. In other words, m of x, expectation of y given x, is the best predictor in the sense that it minimizes the mean squared error. Can we prove this inequality? Well, that is easy. Suppose that you have this left-hand side, and then you subtract m of x and add back m of x to it, then you have this one as your left hand side. If you expand this squared term, then you will have this squared term plus e of mx minus gx squared, and then you will have an covariance term between this part and this part, but that covariance is going to be 0 because we see that this is the CF error or E, and we have seen from the previous lecture that the CF error is uncorrelated with any functions of x, and this is a function of x. So in the end, this covariance term will be 0. So we can just write it as the sum of two expectations. Okay, now notice that this part is squared. Therefore, it will be always positive or equal to 0. From this relationship, you can see that the left-hand side will be always greater or equal to this one. So we have proved this theorem. And notice that this part will be 0 when mx equals to gx. So in other words, when you choose your predictor as your conditional expectation function. Okay, so suppose that now you have an intercept only model. So you don't have x and you have y, and you want to come up with some predictor mu, and you have your prediction error e. What predictor should we use? If we follow this theorem, then it follows directly that the mean should be the best predictor in the sense that it minimizes the mean squared error